All right, so the idea is the objective is to find flexural strengths, okay, flexural strengths of a doubly reinforced section. Now, as usual, you see this notes on the canvas, okay? So if you have trouble follow the write up, don't worry about it. Okay, I have to make the desk stand up so you can see me better, okay? So what is the doubly reinforced section, right? So we have talked about the singly reinforced section and just reinforcing the bottom as tension and concrete as compression, right? So instead of singly reinforced, for the doubly reinforced, we are considering compressive reinforcement, okay? Compressive reinforcement. That means we have steel as part of the compression. We have steel as part of the compression, okay? So first question we're gonna answer here through the first target is, what is this doubly reinforced section and why we need it? Why we need it, right? I mean, if singly reinforced get the job done, why do we need a doubly reinforced section, right? So let's take a look at it. So I have a section, okay? So I have one layer at the bottom here, okay? And I call this AS. And now I have top reinforcement as well, and I call it AS prime compression. And now if I have a concrete cover at the bottom here, and I have a depth of the bottom reinforcement, as I call it D, all right? And I have a depth for the top compressive reinforcement, as I call it D prime. D prime, okay? So I want to show you the difference in terms of strain distribution in the diagram, okay? In terms of strain distribution in the diagram, all right? So let's draw the strain distribution. Now, first of all, for both single reinforced and double reinforced section, the concrete always crushes at 0.003, right? Concrete always crushes 0.003, all right? So let's do a linear line. Let's do a linear line and assume that this dashed line right here, okay, dashed line right here is singly reinforced section, okay? Assume this is only the singly reinforced section, only one layer at the bottom, okay? So as we talked about before, if we have compressive reinforcement, okay, added compression, all right? So the tension side is still the same. The tension side is still the same, okay? So for this case, if we add the top reinforcement, all right, question is, will the compressive zone reduce or increase? Okay, Tyler?
Yeah.
You there? Okay. So the question is, ready for the question? So the question is, if we add compressive reinforcement, will the compressive zone reduce or increase?
It'll increase.
You increase? Think again. Compressive reinforcement.
Then it should increase because it's like taking more to compress it.
Ooh, wait, think about it. So I have now steel added to take care part of the compression with concrete together. So now instead just the concrete take care of the compression, you have also steel to help it. So do you need more concrete or you need less concrete?
Oh, okay, I misunderstood. You'll need less concrete.
Right, you need less concrete, right? So give me 1 second. Okay. So if we have less concrete, right? So if I draw my true strain distribution diagram, it should follow something like this, right? A reduced compressive zone, okay? So that is the actual compressive zone reduced. So when that reduces, when the compressive zone reduces, okay, I actually increased my strain in the tension side, okay? So if the strain, the steel on the tension side increases, right? The strength reduction factor is higher, which means it's more ductile, and it's more safe, right? So the idea of answering why do we need add compressive reinforcement is we want to reduce the compressive zone We want to reduce the compressive zone C, okay? So we increase the strain in the steel, okay? So this is epsilon S. Increase epsilon S, okay? So increase ductility. Increase ductility, okay? So that is phi. Increase phi and less reduction, all right? Hence, we induce an increment in the moment resistance, right? So moment resistance also increases, but not much, okay? Slight increase, not much, okay? So the reason why we need compressive reinforcement is to enhance the ductility of the beam, okay? Ductility of the beam. That's the point, that's the purpose, okay? That's the purpose, is to increase the ductility of the beam. Increase the ductility of the beam. Okay. So once we have compressive reinforcement added, now the strain diagram changes. So corresponding internal stresses and forces also changes, right? Also changes. So let's take a look at the revised or changed strain diagram, right? So let me draw the section here again. Draw the section here again. Okay, that's the concrete section. Okay, concrete section. I have top bars, AS prime, bottom bars, AS. Okay, and the width of the beam is B. Depth of the height of the beam is H. Okay, now the top compressive reinforcement has a depth of D prime, and the bottom tensile reinforcement has a depth of D. Okay, so the strain distribution, just like we drew already, but the strain distribution looks like this. Have a compressive strain and then goes down here. So this is epsilon Cu. And now I want to show you that I do have compressive strain here, epsilon S prime. Okay, and now the compressive zone is C. Compressive zone is C. And the tensile strain here, bottom here, epsilon S. Okay, so now look at the internal stress distribution, right? So draw the stress distribution like this. I have a stress from the steel, Fs, okay? Yield, assume it yields, right? So the compressive block on the top should be a square with a stress block and has a width of 0.85 F prime C, okay? That's the width. And have an effective compressive zone A, still beta 1, C, okay? And now that is the internal stress distribution. But don't forget, I have compressive reinforcement now. The steel also takes compression, right? So don't forget to add a compression from steel, which is Fs prime.
I don't think we can see anything you just wrote.
Let me try it again. Can you guys see it now?
Yeah.
Okay, all right. Sorry about that. Just some problem with software. Okay, hold on 1 second. Let me open up. All right, so where are we at? We're here. Okay. So essentially, we now have the stress distribution, right? Stress distribution. And now the internal force also changes as well, right? So if I draw this internal force, so this is stress, this is strain. I'm drawing the force right now. So the total force from the compression from the concrete still there. So assuming it's A, so here I have CC, and it's at a distance of half A. Okay, and now let me use different color. I want to show to see that I have also a compression from steel, CS. Now that distance from top fiber is D prime. Okay, then I have a tension here. Okay, tension here for the bottom here. Okay, change the color back to blue. Tension here, the bottom here. Okay, so this is force. Okay, so this is force. So the newly added element is the strain of steel. The newly added element is strain of steel, right? So I want to compute the strain of steel. So what I do, I use a triangle, right? I use a triangle here. So epsilon S prime, okay? divided by C minus D prime. Okay, C minus D prime is this fellow here. Okay, equal to epsilon Cu, this fellow here, divided by C, this fellow here. And I can find the strain in the steel, right? Find the strain in the steel in compressive zone, right? So epsilon S prime equal to C minus D prime divided by C, again, multiplied by epsilon Cu. All right, so that is the compressive strain in the steel, okay? Top bar. All right, so now let's take a look at the concrete. So concrete equal to what? Concrete equal to 0.85 F prime C, okay? Beta 1 C B, right? Like before for the Winding stress block. Do you see, do you guys see any problem when I write this? Do you think this makes sense for the concrete compression? Now, I already added compressive reinforcement to it, okay? But I'm using the same old equation as I've used before for the Winding stress block. Do you think that makes sense? Literally, is this right? This right way to write? Sure, you wrote it, right? No, no, this is not right. This is not right because we haven't considered that. Okay, so think of this. I have the cross section, right? Assume previously the compressive zone is here. Okay, that's the compressive zone. And now I have bars. Means a different color that replace part of the concrete. Bars replace part of the concrete. So theoretically, naturally, you need to take this area out. Okay? But we don't take it out here just for convenience purpose. Okay? Why? Because we add it back to the steel. And we take it out from here. So essentially, we assume that is AS prime, okay? AS prime and FS prime. That is steel compression, and we subtract the occupied F prime C, which is the concrete strength, multiplied by AS prime. Okay? We subtract the area that the steel has occupied, right? So in short, this can be written in AS prime, bracket inside FS prime minus 0.85 F prime C. Okay? So that is the compressive forces from the steel. Okay, so once I have the compression from the concrete and compression from the steel, now Fs prime, the stress in the compressive reinforcement has to be recomputed in terms of Young's modulus ES multiplied by epsilon S prime. Okay, but we have to make sure this is smaller than Fy. Why do we want that? We don't want the compressive reinforcement to yield. Okay. At the end, after everything said and done, tension has to equal to compression, which is compression from the concrete and the steel. Okay. So I can further write this out. So tension equals AS Fy. Okay. Tension force from the steel that equals to 0.85 F prime C, beta 1 C, B, that's the concrete part, okay, plus the steel part, which is AS prime, F S prime minus 0.85 F prime C, okay? And pay attention, you do need to compute the compressive stress in the steel, okay? You do need that in the steel, okay? You do need that in the steel. All right, so this is fairly complicated. So that means I have to follow this procedure to compute my compressive stresses first in the steel. Make sure that it does not yield, okay? And I want the tension balance the compression. To obtain the moment. But this whole thing starts with what? It starts with an assumed compressive zone C. Okay, that means I will assume a compressive zone C to start with, and then go through the whole procedure to make sure the tension equal to compression. If it doesn't, I have to go back to adjust my compressive zone C. Okay, so this is a little bit more complicated than singular reinforced. So we have a procedure. Okay, so we have a procedure flow chart as a computer science. Okay, as a computer science, right? So we need the algorithm to find out the actual compressive zone C. All right. So the whole analysis process starts with assume that the strain in the steel tension side, okay, tension side is bigger than epsilon y. That means yielded. Okay. Now, what is the yield strain? What is the yield strain of the steel? Okay. So I'm gonna pick a student now. Justin.
Yes.
Hey, Justin, how are you doing?
Good. How are you?
Good. So, do you recall the yield strain for the rebar for a grade 60? For a grade 60, what is the yield strain for rebar, grade 60?
60 KSI.
That's the strength, close. So Fy equal to 60 KSI. So divided by Young's yes equal to 29,000 KSI. Roughly equal to what? 0.00, give you a hint, 2 plus 2 digits.
Let me try it.
Okay.
2-1.
1, right? That's good. So gotta remember this, okay? Gotta remember this. Okay? Have to remember this, okay? So the yield strain of the bar, grade 60, always 0.021, okay? We always use that to compare, to make sure that my tension side reinforcement yielded, okay? Tension side reinforcement yielded. Okay, so now we start from that. We start from the first assumption that the tension side of bar yield. Start from there, okay? Then what we do is we're gonna try, okay, we're gonna select a compressive zone C. Select a compressive zone C, okay? Just arbitrary values, but not so arbitrary, We usually select it to be between, okay, between D over 4 or D over 3, okay? Third of the depth or quarter of the depth, we select the value in between these two, upper bounds and lower bound, okay? Okay, now we select the C, and then we can proceed to calculate the strain in a compressive reinforcement. Epsilon S prime equal to C minus D prime divided by C multiplied by epsilon CU. Okay, so quick question. What is the compressive strain for the concrete? What is epsilon CU? Ben?
0.003.
Great. Okay, don't forget, okay? That is the compressive strain for the concrete. Now, with that, I can get my compressive strain in the steel and proceed to get my compressive stress, Fs prime, equal to Young's modulus ES and multiplied by epsilon S prime, okay? And I have to make sure that that is smaller than the yield strength of the steel. Why? Because I don't want my compressive reinforcement. To yield. Okay. I only want the tension side to yield, but not the compression side. Okay. So once I finish that, I will go on to check my compressive forces from the steel. That is AS prime, FS prime minus 0.85 F prime C. Okay. That will replace.
You want the compressive side to yield also.
Say it again, sir.
Why don't you want the compressive side or compressive steel to yield also?
So think of it, right? If the compressive side of reinforcement yielded, right? So have you seen the steel structure yield before? A bar just compressed? Okay, so think about it, right? If you have a fence, say a fence, steel-made post, right? If you compress it, what it does? Will it bend or will it stay straight? Okay.
Or it bends also.
Right, it bends, right? So it will buckle, have a very large deformation, isn't it? Right? So you actually have a lateral deformation that will crush the concrete in that direction.
Okay, I see now.
Yeah, right. So we don't want it to ever yield. So the compressive reinforcement is just stating as elastomer, elastic materials there. Okay, we only want the tension side to yield because as tension happens, the concrete will lose strength. Only the steel will take care of the tension force, and we can let it yield because stretching will not cause lateral deformation so much, isn't it?
Yeah.
Yeah. So now I compute my compressive forces, and I can proceed to compute my compressive force from the concrete CC, which is 0.85 F prime C, 0.85 F prime C B, that's the width, and B the 1C. Okay, that's step number 6. Okay, and once I have the compression force from the bar, compression force from the concrete, I can also find out the tension force on the bottom bar, which is ASFY. Okay. So I have the tension, I have the compression, so I come to a decision-making step that whether my tension equal to compression, right? So is this true? Right? If I got lucky, I said yes. If the mattress tension balance out the compression, so everything's good, right? So I will just move forward to say, okay, let's check the steel and the tension side. And that is D minus C divided by C multiplied by epsilon Cu. I have to make sure the tension side yield. Make sure the tension side yield. And then I will get my moment capacity Mn using that old-fashioned equation, compression multiplied by D depth minus half A plus compression from the steel D minus D prime. That's new. Okay, that's new. Before, we only have the compression multiplied the D minus half A part. But now, as the compressive reinforcement is added, you need to consider the contribution from the compression force. Okay, just to clear, right? Just to clear. Now, how do we sum the moment, right? Think about it. This is CS from the steel, and this is CC, and this is tension T. So we sum the moment with respect to the tension point, right? So here, this is D minus half A, okay? And here, this is D minus D prime. Okay, that's how we sum the moment. All right, okay, so that's if we're lucky, right? That's if we're lucky, right? So this, don't forget, is under the condition that if it's satisfied, the tension equal to compression criterion, all right? If it's satisfied. If it doesn't, they have two routes. So first route, so if tension is greater than compression. So we need more compression, right? We need more compression. So how do we find more compression? Should we go all the way back? Yeah, right? We should go all the way back, all the way back, all the way back to reselect my compressive zone. So in the case, remember this is tension greater than compression, right? In tension greater than compression, I need more compression. Should I increase C or decrease C? Bryce?
Yes. Yes. Hey,
Increase or decrease C here?
you should increase it.
Increase it, right? Because I want to have more compression, right?
Yep.
Right, that's a great answer, thanks, sir. So increase C, okay? And go through the whole loop again, right? Go through from 2, 3, 4, 5, 6, 7, 8, right? Now, if it goes the other way, if tension is smaller than compression, right? Tension smaller than compression, I have all the way, I have to go all the way back again to step 2 again. So tension smaller than compression, what I do? Megan?
You would decrease C.
Decrease C, right? That's a great answer. Thank you very much. Decrease C, right? Now I go through the whole loop again. Okay? Can you see it? All right? So that is the procedure. Pretty long, isn't it? Pretty long. Okay? So iterations often required. Okay? So that seems to be very long, but don't worry, right? Let's walk you through an example, right? Let's walk you through an example. Okay, so example, okay, example. Okay, and now I have a section. Okay, I have a rectangular section, nice rectangular section. Okay, now for this rectangular section, I have top bars. Okay, top bars. Now this is compressive reinforcement. Okay, compressive reinforcement. Okay, and these are 3 number 9. All right, quick check. Lucas, what is the cross-section area for number 9 bars?
1.
1 inch square, right? That's correct. Yep. So now I have a 6 number 9 bars. 6 number 9 bars. The bottom is tension side, right? So the total height of the section, 20 inches. Okay, and the concrete depth for the compressive side, D prime, is 2.5 inch. Okay, and now the bottom layer, okay, should I put DT or DS here? Should I put DT or DS here? Jack, Mr. Meadows, Jack?
Yep, I'm here.
Or DS here?
On the bottom one,
Yes.
DS or DT.
Okay, second chance, got it right. Thanks.
Yeah.
So right? So happen to be this is 17.5 inch. Okay, and I saved you the trouble. I actually calculate the center for you for the group of bars. Okay, and this is DS. This is DS, and that is 16.8 inches. Okay, and in the exam you might have to calculate yourself. Okay, in the exam you have to calculate yourself. Okay, all right. So several more parameters. Concrete strength is 4 KSI. Concrete strength is 4 KSI. Grade 60, that means the steel yielded at 60 KSI. And I naturally know that my beta 1 strength reduction factor is dependent on the concrete strength 4 KSI. Michael, my current.
Yeah.
What would be my beta 1 value here? 0. Consider it's a 4 KSI concrete.
8.5.
Right, that's great. That's correct answer. Okay, so that is the wind stress coefficient, right? So the Young's modulus for steel is 29,000 KSI. Always remember that. Okay, so that's all the parameters I need to know. Okay, I need to know to solve the problem before, and also I definitely need to know the width of the concrete is 12 inches. Okay, so let's solve the problem, right? Let's solve the problem. So solve the problem. Okay, let's follow the flow chart, right? Let's follow the flow chart. So take a quick look at flow charts first. A is to assume the tension side yield. Fine. So let's do that. So first step, assume tension side yield, right? That means epsilon S equal to epsilon Y and Fs equal to Fs equal to Fy, epsilon S bigger than equal to epsilon Y. Okay. And then second step, we need to select the C. All right. So pay attention. We always to try the first value, we select the C that between 1/3 of the depth and 1/4 of the quarter of the depth. Okay, can I get a quick calculation? What is a quarter of D here? Okay, and this D here is DS. Okay, can I get a quick calculation? What is D here? 16.8 divided by 4. Daniel, can I get a quick calculation? What is the quarter of the depth here? Daniel, can you hear me?
Yeah, here. Sorry, just doing it.
So what is the quarter of the depth here? Can I get some number? Quick calculation.
4.2.
4.2. Great. How about the third of it? Third of it.
5.6.
5.6. That's wonderful. Okay. Thanks a lot. All right. So we're going to select a value between them. So let's try. We're just going to blind try. Okay. C equal to 5 inch. Different from last lecture, this lecture, I totally don't know. I'm in the blind, okay? Let's just try some number, right? Just want to try some number. So that's the compressive zone, I picked that, okay? So the next step, I'm gonna write here. So the next step, how about my compressive strain, epsilon S prime, okay? So epsilon S prime equal to C, which is the actual compressive zone, minus D prime here, okay? Divided by C, multiplied by epsilon CU. So 5, I try this value, 2.5, I know, divided by 5, I try, and then 0.003, and I got a 0.0015. So this value here, okay, Marshall, Mr. Woods, Marshall.
Yeah.
So can you tell me if this strain is bigger than yield strain or smaller than yield strain?
Let's see. That is going to be. It's smaller.
Smaller, right? That's the bingo.
Yeah.
Right? Thanks a lot. So this is 0.0021, right? So we got it satisfied. So now yield it. Okay.
2.1 instead of 2.07.
I just rounded up. Okay.
Oh, okay.
That's accurate. Thanks. Appreciate it. That's good. Okay. So this means good. All right. So it does not yield. We like that. Right. Then we proceed to find the stress in the compressive reinforcement. Fs prime equal to ES modulus multiplied by epsilon S prime. That is 29,000 KSI. Pretty big. Okay. For the modulus. Multiplied by 0.0015. All right. And I got 43.5 KSI. 43.5 KSI. So that's the compressive stress. Okay, you can double check, right? This is actually smaller than 60 KSI, which is Fy. Okay, so it's okay, right? So it's okay. Double check is okay. All right, but nevertheless, now I have all these. I want to find out the compressive force from the bar. So CS equal to ES prime multiplied by Fs prime minus 0.85 F prime C. Okay, so what is the compressive area? What is the area of compressive reinforcement? Adam. So how many bars I have in the compressive zone? How many bars?
Do you not have bars in the compressive?
How many bars? How many bars I have in the compressive zone?
Don't you not want the steel bars in compressive?
Yes, but how many?
6.
6? You sure?
Or would it be all of them? 9?
9? Are you sure?
No.
All right, you're not sure, right? So think about it. And these bars at the bottom, they take care of tension or compression.
They'd be taking the tension.
Right, so these are tension bars, okay?
So it'd be the 3 up top.
Right, that's right. So these are
Okay,
things.
that makes sense.
Yes, makes sense. So these are the compression bars, okay? I know we forgot, so that's okay. Just remind us, all right? So I have how many bars again, Adam?
3.
3. So what's the area? Number 9, so I have what?
An inch? No,
What's the area for number 9 bar?
that'd be
Number 9 is a wholesome number, great number. Number 9, 1,
2 inches squared.
1 inch squared, okay?
1 inch squared.
Remember this, okay? Gotta remember this, all right? So it's 1 inch squared for number 9 bars, always, okay? All right, good deal. Okay. So carry on. I now have the compressive stress calculated, and this is just from fresh memory, 43.5 KSI. Okay, 43.5 KSI minus 0.85 divided by multiplied by 4. Okay, and then I got a total number to be 120 kips. Okay, 120 kips, and that is the compression force. Compression force. All right, from steel. Now from the concrete, CC equal to 0.85 F prime C in B, either 1 C. So 0.85 prime C is 4 KSI, and 12 inch of a width, that is B, multiplied by 0.85, okay, and multiplied by 5 inch, that's the compressive zone C I selected, okay, don't forget. So this will come up to be 173 kips. Okay. So now I have total compression. So just check step number 7, right? Is T equal to ASFY? T equal to ASFY, right? Now that is how much of a tension reinforcement I have. Dalton, Mr. Brown. Dalton. Mr. Brown, can you hear me? Oops. Okay, Dalton just left. All right, maybe bad connection. All right, my next on the list, Brett.
Yes, hello.
All right, so what is the reinforcement intention area for reinforcement intention here? So first of all, how many bars I have in the tension side? Can you see?
6.
6, right? What is the area for number 9 bars?
1 inch.
1 inch. So 6 inches, right? Is that right?
Yes.
Okay, that's good. Okay, now a trick question, okay? Thanks a lot, Brian. That's right answer. So 6 inches multiplied 60 KSI, that's the yield strength. I got a 360 kips of total tension. That's the total tension. All right. So naturally, next step, I'm gonna judge whether the compression balance out the tension. So the total compression come out to be 293 kips, which is apparently smaller than the tension side. Okay. So it's smaller. Should I go towards the left to decrease? So this is I wrote the other way, but if the compression is smaller than tension, should I go to increase compressive zone or decrease compressive zone? The next question goes to Austin Weicker. Austin.
Yes, I'm here.
Yeah, so I have a scenario here that compression from concrete and steel is smaller than the total tension. Should I increase my compressive zone, C, or decrease it?
You'll want to increase the compressive zone.
That's right. That's great. Thanks a lot. So now I have to increase my compressive zone C, right? And Austin, don't want to let you go yet, sir. So if I increase C, what should I do then afterwards? What's the next step?
Don't you just have to solve it back through from that step 2?
I have to do it all over again, right? Do you like to do it all over again?
I'd prefer not to, but
we prefer not to, right? That's a good answer. Me neither, right? Nobody want to do that. Okay, so that's long, right? That's a long solution. Thanks a lot, Austin. So that's a very long solution. So to shorten it, of course we had to do it because we're civil engineer, right? We had to find out the moment capacity. Okay, so but to shorten the process, right? To shorten the process, okay, what we're gonna do? We have to establish a table. Okay, so let us use a table. Let's use a table. To do
so do you just go back and forth until they equal each other?
That's right. That's correct.
Okay.
Right. That's why we have to iterate. Okay. So
Do they, Bob, I have a question.
Yeah, go ahead.
Does the tension and compression have to exactly equal each other, or is there like a forgiveness area?
So that's the difference. Can you see
Gotcha.
it?
Yeah.
Okay? Yeah. We're gonna talk about it. Okay. That's good answer. Great answer. I mean question. Sorry. So we're gonna use a table. Okay. And this is how the table looks like. I'm going to list my variables on the very left. So this is the compressive zone C. Okay. And I have my strain, compressive strain epsilon S prime equal to C minus D prime divided by C and multiply epsilon CU. Okay, I'm going to list my compressive stresses as well equal to ES epsilon S prime. Okay, I'm going to compute the total compression from the bar AS prime multiply FS prime minus 0.85 F prime C. I'm also going to compute my compression from the concrete. That is 0.85 F prime C, B, beta 1, C. And then I list my tension T equal to ASFY. Okay? And then at the end of it, I want to check if the tension equal to CS plus CC, so I need the total compression as well. Okay? So that is the table. That is the table, okay? So it doesn't look like a table yet. So let me move on to the left side and establish the grid like this. Okay? A grid like this. Okay? Okay, so I started filling the numbers. Now we just tried 5 inches. We just tried 5 inches, right? So I'm gonna list the 5-inch number here, okay? And apparently 5 inch does not work. Okay, 5 inch does not work, okay? I can write down this is 0.0015 strain and 43 KSI, okay? CS equal to, what is my CS here? CS is 120 kips. Okay, CC is what? 173 kips. So the tension is 360, and I come up short. My compression is only 293. Okay. So that apparently, so T equal to CS or, sorry, CS plus CC or not, right? So the first case tells me does not, okay, or MG, right? No good. What is the criteria? This is bigger, much bigger than 5%, much bigger than 5%. Okay, so it does not work. Okay, then what we're gonna do is we're gonna lift 5.5 inch. I'm gonna try 5.5 inch. Okay, why? I just have to increase, right? I just said I have to increase, so I went up to 5.5 inch. Okay, so first of all, I need some help here. I need some help here. I need someone help me to calculate. I need someone to help me to calculate the compressive strain epsilon S prime. All right, so I'm gonna pick my next victim, okay? Peter, Mr. Schenker. Peter.
Yeah, sorry, I'm a little distracted right now. I spilled a bunch of tea on my floor. I'm just trying to clean it up.
That's all right. So let me walk you through, right? So we're going to increase the compressive zone size from 5 inch to 5.5 inch. Okay? You got that?
Yeah.
Okay. I'm going to use this equation to compute the strain in the steel, all right? So can you help me punch in the calculator, tell me the number?
Hey, could you repeat that? You're getting choppy.
Okay. So I'm going to use my compressive zone, increase compressive of 5.5 inch to compute the compressive strain epsilon S prime. Okay? Use this.
Okay.
So can you punch in the calculator, tell me the number here?
What is 5.5 in that equation?
What do you think?
Is it, oh. Yep.
So let's take out your calculator and do it, right? So this is 5.5 minus d prime is 2.5 divided by 5.5 and multiplied by 0.003. What do you get? Yeah.
You get 181.81.
Say it again?
181.81.
It doesn't sound right. Think about it again, right?
5 minus 2.5 divided by 5.5 divided by 0.003.
Not divide, multiply.
Ah.
Try it again. So 5.5 minus 2.5.
0.001.
Right? So 0.001, right? Can I get the last two digits as well?
6.3.
Great. Thanks. That's the correct answer. Okay. Thanks, Peter. All right. We got the strain, right? So I need to compute the compressive stress. Noah.
Yeah.
Hey, how are you doing, man?
I'm doing.
Okay, well, that's good. I'd like to hear that, okay? So I'm going to compute. I need your help to compute the compressive stress in the steel, okay? So I'll give you some number. I'm going to use 29,000 KSI. That's the Young's modulus. So multiplied by the strain I just got from Peter, 0.00163. Can you punch it in to get me a number for it?
0.001. Yeah, 47.27.
Great. Let me write it down here again. So how much again? 47 point?
I got 47.27.
That's great. So quick answer, or quick question here. Is it smaller than yield strength of steel or higher?
Should be smaller.
All right. So it does not yield, isn't it?
Yeah.
Is it good for us or bad for us?
Good.
All right. That's good answer. Thanks a lot. Okay. Right. So we're good. All right. So that's a 47.27 PSI. Okay. So I got the strain. I got the stress. I'm going to save you a hustle. I got this number pre-calculated myself. So that's 132 kips I got for the compression force from the steel, and 191 kips I got from the concrete, okay? And compared to the 360 kips, I still come up different, okay? Because I got now 323 kips, still short, okay? So this is no good, okay? And this is no good, okay? And error is about 10%, So it's bigger than 10%, so not good, not good. So as I was frustrated, I said, okay, one more try, right? Let's try 6 inches. quite 6 inches. Okay, and now I want to save you the hustle, and this is the quiz. Again, I'm going to leave the quiz as text entry, okay? Text entry. I need the compressive strain and compressive stress for this case, okay? Everybody, I need these 2 values, okay? I'm going to leave a quiz in the text entry format, okay? But to save you the hustle, I pre-compute all the other numbers. So this is 142 kips for the CS, 208 kips for the CC, and 360 for the tension again, and I come up good. I now have a total compression of 350 kips. Now this is only about 3% error, so great, working okay, because this is less than 3% error, which is less than 5. Okay, so I got it right in the last round. Right?
I thought the limit was between 4.2 and 5.6.
Yes, you are absolutely right, but that's an initial try.
Oh, okay.
That's an initial try. You're absolutely right. This 6 inch, you can see that, like you said, slightly larger than expected value, right? But as I said again, that range is for initial trial. You end up something different. Okay? All right? Right, now you may come and ask me again, so, okay, so Bob, your final answer is out of the range. Why you choose a number from that range anyway? Because most of the beams, most of the time, it falls in that range. We just got lucky this time. Okay? Clear? All right, so I assume you're okay. If you have more questions, we can continue, okay? So let me quickly wrap up. So once I have this satisfied, I'm good, right? So I'm gonna check again, don't forget, I'm gonna check again my steel, right? So check steel again, epsilon s again, okay? So now the strain is still epsilon s equal d minus c divided by c multiplied by epsilon cu, so that is 16.8 minus 6 inch, we just found out, divided by 6 multiplied by 0.3, that's our 0.003, and that is 0.054, which is much greater than the 207 values, okay? So, all right, so the rest is, finding the moment capacity. We're gonna finish that in the beginning of Thursday's lecture, okay? We're gonna finish that beginning of Thursday's lecture. But that's all we have to do for the doubly reinforced section. Okay, before I let you go, any questions? Any questions, guys? Any questions? Are we good? Okay, I'm gonna assume we're okay for now. If you have more questions, we can meet on Thursday. And just so you know, we're posting our homework. We will post our homework solutions, okay? So when you get a time, download the homework solution, compare that with your homework solutions, and you can see where the mistakes are made, all right? Okay, so our time's up today. Question?
Yeah, I have a question about the homework.
Go ahead.